Today, we'll be having Thomas Brazelton speaking to us about abstract enumerative geometry.
Awesome. Cool. Thank you so much, Sarah, for having me. And thank you, everyone, for coming. So yeah, I'm excited to talk about abstract enumerative geometry. So I think some people in the audience will be familiar with one of the things that I'm going to be talking about, which is sort of enumerative geometry with a little bit more of a motivic flavor. So I'm excited to sort of tell you about some of the questions and some of the progress that's been happening in that area. And then sort of hopefully for the back half of the talk, I'm going to be able to tell you about some of the things I'm thinking about now, which is taking enumerative geometry in a little bit more of an equivariant direction. But before I do that, so let me start talking about enumerative geometry. So enumerative geometry classically, it asks questions of the form, how many, and expects integer answers. So we're looking for these sort of like geometric questions that hopefully will have interesting answers. And by interesting, I mean, they're not zero, they're not infinite. It's sort of something in between. We have a finite amount of data that we can kind of latch onto and study. So a good example of this dates back to Apollonius in around 200 BC. And the question was, sorry, my pen is acting super weird. Given 3 circles on the plane, how many are tangent to all 3? So here's where like having an iPad is super going to come into play. So I don't have to embarrass myself by trying to draw circles, although that was embarrassing. Okay. So we've got 3 circles that we start out with, drawing them on the plane, and we're looking for circles that are going to be tangent to all 3. So it's a really fun thing to do this if you haven't before, to try to sort of see what the symmetries are that are hanging around and what types of circles we can draw that are tangent to all 3. So I've always sort of got one in the middle. Maybe I've got one on the outside intersecting all 3, and I've got other types of circles. Another example that's due to Bézieux in 1779 is the following. Given planar curves of degrees m and n, at how many points do they intersect? Okay, so we can think about maybe drawing something like this and drawing something like that, and then labeling all these different points of intersection. So by planar curve, if you're not familiar with this, I'm talking about we're living in projective 2 space. So we want to projectivize so that we have a nice geometry, and we're looking at the vanishing locus of a homogeneous polynomial of a certain degree. And maybe one more example that I want to talk about is from Salmon and Cayley in 1849, or right around then, which is how many lines lie on a smooth cubic surface. So cubic surface here, this is going to be a vanishing locus of a degree 3 homogeneous polynomial in x0 through x3. And we think about these x0 through x3, these 4 variables, as being in complex projective 3 space. So I have an example that someone gave me, which is this 3D printed cubic, which is maybe familiar to people who work in algebraic geometry. This is a Clebsch cubic. And this thing is special because it's actually symmetric in all the variables. So I've got x0 cubed plus x1 cubed plus x2 cubed plus x3 cubed is going to be equal to the sum of all these cubed. So this is in CP3. So obviously we can't visualize this. This is going to be some 4-dimensional object in 6-dimensional space. what we tend to do, and one of the reasons that we like having symmetric cubic surfaces is that on affine charts, they all look the same. So I can set one of these variables equal to 1, and then I can graph this thing now living in complex 3 space. Again, we can't visualize that, but maybe we could graph its real points, and then you're going to get something that looks like this. Okay. So the cool thing about this is that all of these questions over the complex numbers have well-defined answers. So the answer to Apollonius's problem is that you have 8 circles, which are going to be tangent to all 3. Obviously, you want to avoid some generic situations like when you picked all 3 circles to be the same. In that case, I'm going to have like infinitely many things tangent to them. But sort of like with probability 0, that's never going to happen. The answer to Bezout's question is going to have m times n points. And we should really clarify here. These are counted with multiplicity. And for this question, I should say what I mean by how many lines. What I mean on the cubic surface is that a line should be something like I'm standing on the cubic and I can walk along the cubic surface in such a way that I trace out a straight line through 3 space. That's geometrically what we mean. Algebraically, what we mean is how many equations for lines in CP3 are valid when you plug them into the equation for the cubic surface. And the answer here is you always have 27 lines. And again, all 3 of these solutions I'm talking about happening over the complex numbers. Okay, so let me sort of say, how do you solve an enumerative problem? And because this is a topology talk, we should expect some topology to come into this. There are algebraic ways to approach a lot of these things, but I'm going to try to keep it pretty topological. So step 1 would be to find a moduli space of possible solutions. And maybe let me drag some stuff around. So I'm going to try to keep a running example for the lines on a cubic surface over on the right here. So if I'm looking for lines on a complex cubic surface, I want to look at all the lines in CP3 that could lie on the surface, but also might not. So let me call this moduli space a complex Grassmannian of lines in CP3. And this is a type of topological object that we know and love. Number 2, and this is sort of the hard part, is we want to encode the enumerative problem as a vector bundle. So in this case, I won't explain in detail what this is, but basically I've got this moduli space of lines on a cubic surface. Because this is a moduli space, it has a tautological bundle that you would call S. So the fiber over this is the line it represents. And I can dualize this thing. And I can take a third symmetric power of this. So this is some algebraic vector bundle. And if I have a given cubic surface X, it'll define for me a section sigma X. And here's what this section is going to do. It's basically just going to plug in the equation for the line. So sigma X of L is going to be equal to 0 if and only if L lies on the cubic. So here, this thing is a line, and this is some fixed cubic surface. Okay, so once we have this, the third step is I want to count zeros of a generic section with multiplicity. So I want to really study this object, which is the 0 locus of some sigma X. So there's this theorem that we maybe know from Botten 2 or from some other book about sort of this classical topology that you might call the Poincare-Hop theorem. And it's the following. So given a rank n vector bundle, over, let's say, a smooth compact n manifold, And then let me write also, so plus orientation data. And I'll clarify what I mean by that in a second. So if we have this setting, then here's what I can do. I can say I have a certain characteristic number. I'm differentiating between a characteristic class and a characteristic number, as like a class lives in a cohomology group. And that number is like maybe when you integrate that form on the manifold. I can do something like this. So sorry, and let me also say, and a section, sigma from M up to E. I can take an Euler class or like an Euler number, and this can be computed by looking at all the points in the zero locus of sigma and recording some local index of the section at that point. So what should this local index be? We should think about maybe if I look around the point, I can take germs of this section and I can ask maybe what's the multiplicity of vanishing, or what's the Brouwer degree of some intrinsic derivative of this section at this point. And that's exactly what this local index encodes. So over C, the index of sigma at some isolated point is just the multiplicity of sigma at P. So the really cool thing here is that this thing on the left didn't depend on the choice of sigma, right? It's some characteristic class that's completely invariant of the section that you picked. But for a generic section, it has this really cool interpretation as you're really counting the zero locus together with multiplicity. So what I could do is I could by, Churn classes, or I learned on Monday, you can do this using Schubert calculus if you want to. I could compute that the third symmetric power of the dual tautological bundle is 27. And this is, again, independent of any choice of section. So this tells me then for any cubic surface, it has 27 lines. Counts it with multiplicity. So let me say two quick things about this. The orientation data we don't care about over the complex numbers. Our base manifold is oriented, the bundle is oriented, totally fine. Over the reals, if both things are oriented, you can get an analogous statement. You can actually get away with slightly weaker orientation data. There's a notion of relative orientation, which is due to Okonek and Telemann. And it's sort of talking about a bundle maybe not being oriented over an orientable base, but being compatibly oriented over its base in some suitable way. And then maybe let me also say, if I don't have a generic section, when I look at its zero locus, it might not just break up into a loose collection of points. There might be higher dimensional components to the zero locus. And you can actually still make sense of what a local index means here. This is this theory of residual intersection. There's like an awesome Wikipedia page about it. Dan Quillen actually wrote some stuff about it after he studied with Grothendieck for a year. So there's like a really cool literature around that type of stuff. Okay.
Can I ask maybe an unimportant question?
Go for it.
So just how do you formulate this notion of a generic section in this context? Is this like there's some space of sections and you can sort of perturb in that space, like you have these methods?
Basically, yeah.
Okay.
There should be some very low dimensional collection of non-generic sections, and yeah. Maybe the loosest way to say it is just pick one at random. It'll be generic. Okay. So over other fields, so let me say, let me maybe name this thing. This is what Schubert would have called conservation of number. So the story goes that Poncelet, who was a French mathematician, thought this should work, called it principle of conservation or like continuity of number, and then everyone hated it. So Schubert came back 50 years later, just rebranded it, and he's like, we're going to call this conservation of number, and then it worked and everybody liked it. So this is what Schubert would have called conservation of number. And the sort of big idea is that conservation of number breaks over other fields. So it no longer remains true. But it can be repaired using motivic homotopy theory. So I'm going to avoid doing what everyone does when they bring up motivic homotopy theory in a talk, which is like build the motivic category, tell you there's bigraded spheres and like do all that nonsense. I'm just going to say it exists. You can do a homotopy theory for varieties, and we can talk about it later if you want. But there's this theorem now that was floating around in the ether for a bit, but the most concrete and sort of most general statement of it is due to Bachman and Wickelgren, which is given any rank n vector bundle over a smooth compact K variety of dimension n. Again, let me say plus orientation data. Sorry. And a section sigma. Its Euler number. So let me maybe like underline this and put it in quotes. Can be computed as follows. So I'm going to take some Euler number of my section, and I can do this exact same thing. I'm going to sum over points in the zero locus, and I'm going to take a local index. The reason that this thing is different is that these are no longer integers anymore. So these things, these are now symmetric bilinear forms. Over your ground field K. So over the reals, there was this sort of weird thing that happens where I could pick a certain section, or maybe I could multiply that whole section by -1. And my local index would sort of pick up this factor of -1 by flipping orientation. So I had this weird orientation stuff that messed up everything over the reals. And the idea is sort of once you fix orientation data, you can really repair this, and you can get a well-defined symmetric bilinear form that is a solution to this thing. So let me explain sort of why this is interesting over the reals. And the reason it's interesting is that sort of we should pick up strictly more information from a symmetric bilinear form than just a number. So given a line on a real cubic, so I'll say cubic means cubic surface. So given a line on a real cubic, it defines a loop in the frame bundle. So over the complex numbers, right, the frame bundle of the cubic surface is going to be U of 3, and its pi1 vanishes, so there's nothing interesting to say here. Over the reals, we actually have that pi1 of SO3 is Z mod 2. So I have two classes of lines. I've got something that you might call hyperbolic lines, and I've got something that you would call elliptic lines. So the thing here is, like, if I take a line on a cubic surface, we can look at the tangent plane of that line. And as I travel along the cubic surface, the tangent plane is going to wiggle. And because we're projected, we're going to come back along the same line. And that plane will either come back exactly the same that it was, or it'll come back flipped. And that's exactly what these two classes of lines are. So there's a theorem which dates back to work of Segre in the 1940s. We should also probably write Nash and Kharlamov, Okonek and Telemann, and Cass and Wickelgren, which says the following: the number of real hyperbolic lines minus the number of real elliptic lines is always equal to 3. So this tells you that on a real cubic surface, we have at least 3 lines, and these are all going to be hyperbolic, and we might have more elliptic lines and more hyperbolic lines, but they sort of come in pairs past that point. And then, so the reason that this works basically is that in this paper of Cass and Wickelgren, they computed this enriched Euler number, and they got a matrix that has 15 ones and 12 minus ones along the diagonal. That rank is 27. That's recovering this classical count of the complex numbers. And the signature, if you look at the difference between the ones and minus ones, is always going to be equal to 3. So there's a further theorem that's due to Cass and Wickelgren, which says basically we can now do this over any perfect field, pretty much. So not just the complex numbers and not just the reals, because we have motivic homotopy theory, we actually have a notion of doing homotopy theory over things like finite fields. So over FQ, there is a further constraint on the residue fields that lines are allowed to be defined over. And maybe I won't say any more detail about that. I'm just going to sort of leave it like that. Okay, so this is a whole program of math that you would call A1 enumerative geometry. And the idea here is to use tools from motivic homotopy theory, or A1 homotopy theory, to solve enumerative problems. And then interpret them, or interpret your solutions. So the idea is that you set up a problem much in the same way that you would. You get a symmetric bilinear form that's defined over some very ambiguous field K that maybe you haven't specified. And then if you pick a K, which is maybe a more complicated field, and by complicated, I mean like a tau cohomological dimension, you're going to see more and more invariants that you need to classify symmetric bilinear forms. And each of those invariants should encode something interesting that's happening with the underlying geometry. So there's this really cool stuff that becomes visible when we start changing up the fields that we weren't able to see over the complex numbers. So when I say tools here, maybe let me say a little bit about what I mean. When we had this section of a vector bundle, we talked about taking a Brouwer degree of its intrinsic derivative. In this setting, we need a notion of Brouwer degree that holds in motivic homotopy theory. So one of the tools that we like to use is Morel's Brouwer degree. So it's a way to take a map maybe from like affine n space to itself and produce a symmetric bilinear form. I know there's like a few people in the audience who have worked with this stuff in detail. There also are other tools. There's a Schubert calculus valued in Chow-Witt rings that's due to Matthias Wendt. There's a notion of residual intersection that holds in motivic homotopy theory that's due to like a ton of people. But maybe I'll say sort of most of my work up to this point has been dealing with this Brouwer degree and trying to make it like a more tractable computational thing for enumerative geometers. And I love talking about it. So if you have any questions, you should ask me about it. Okay, so I'm going to switch it up and talk about enumerative stuff in the equivariant context. Before I do that, maybe I should stop and see if there are any questions. Okay, if not, I'm going to take a, yeah, go for it.
Since you said you love talking about Morel's Brouwer degree, and I have
Yeah.
no clue what that is, can you say something about it in, I don't know, as layperson terms as possible?
Yes, yeah, I'll give you like a 30-second pitch, which basically is if I have a map from affine n space to itself, so this is given by some polynomials f1 through fn. What I want to do if I have a point mapping to 0, right? Classically, if I have what I should do is I should take a little neighborhood around P and I should map it to a little neighborhood around 0. And then I should co-fiber out by their boundaries and I get an induced map of spheres. And the thing is you can do kind of a similar thing here. So I can sort of delete the point, I can co-fiber out by its complement. And I get an induced map here. And this lives really, if you're a homotopy theorist, this should live in like the 0th stable stem motivically. If you're not a homotopy theorist, let me just say that I can take the defining K algebra for this map, which is I'm just going to take like global sections and map mod out by this f1 through fn. And there's really like a very natural quadratic duality on this thing that is like a symmetric bilinear form that encodes a lot of its properties, and it's exactly this thing. So from a homotopy theory standpoint, you're able to talk about like an induced map of spheres, and then so this should really be localized at the point. From a commutative algebra standpoint, there's like things that you can do with this algebra with a computer that give you a matrix. But yeah, so we should just think about it as like a Brauer degree, but for varieties.
Okay, cool, thanks.
Yeah, for sure. Okay, so let's switch it up and let's talk about a sort of new direction that I'm calling.
I'm sorry, Tommy, can I ask a quick question?
Yeah, go for it.
Just because you said the word, I'm not sure exactly what you mean by cofiber out. Can you like say what you mean by that?
Yes, literally take this thing, include it in that thing, and take the associated cofiber sequence, which is like super not something you can do in the world of varieties. Like you should not just be able to like take colimits as freely as we can do that in topological spaces. You really need to be like in a motivic context to make sense of this object. Yeah, it's a good question.
Thank you.
Okay. So equivariant enumerative geometry. And let me say sort of for this whole section, we're going to be talking about over the complex numbers. So we're not going to switch up the field at all. So, so if I have a, so let me ask this question, given a symmetric, which should have two M's, cubic surface. So by symmetric, what I mean is that it's defined maybe by a symmetric polynomial. So something like the Klepsch cubic had this symmetry. Symmetric also, I mean, right, like I have an S4 action on CP3 that permutes your coordinates around, and I want this action to send the cubic surface back to itself. One of these things, like we see this sort of threefold symmetry right here as I rotate this. This is coming from like fixing one coordinate and letting those other three coordinates rotate around. There really should be like a fourfold symmetry that we're not able to see. So given a symmetric cubic surface, its lines have S4 orbits. So every line on my cubic surface, now if I start acting via S4, that line is also defined by something, well, not necessarily symmetric, but it's defined by something that should map to another line on the cubic surface under this S4 action. And then a question you can ask is basically just, what are these orbits? So this leads you to sort of this program that I'm calling equivariant enumerative geometry, which is to ask enumerative problems in the presence of symmetry. And get answers. My answers really should be sums of orbits under S4, right? So I should have each collection of lines should be some transitive S4 set, right? It should be some orbit under S4. And there's a really natural place for these things to live, which is basically just the free abelian group on orbits, which is the Burnside ring. So this program is we want to get a well-defined answer in the Burnside ring. And I want to be able to not only answer this question, but I want to be able to say something like the question actually doesn't depend on the symmetric cubic surface. I'll get some answer in the Burnside ring that is completely invariant of the choice. It should hold for any symmetry. So this is like a cool direction that I like a lot, because there's really no reason to expect that enumerative answers should respect the ambient symmetry of something that you're looking at. And the kind of surprising thing is that they do. So let me try to talk a little bit about the technical details of this, just because I think it might be interesting for some of the people who are working in equivariant stuff here. So the idea here is that we want to prove something that feels like conservation of number in the equivariant context. The problem is, if you go to Botan 2 and look at how they prove conservation of number, they are dealing with transversality. They're taking like a section of a vector bundle, having it be transverse to the zero section. And for the equivariant people in the audience, we know that like equivariance and transversality don't mix, and we really just don't want to talk about those things together. So we do sort of a slightly different thing, which is we want to get a formalism for cohomology classes, and we want to demonstrate basically that cohomology classes can be decomposed and computed. So we're going to think about this thing of like an Euler number as a sum of local indices in like a slightly different way. We're going to think about it as it's some global cohomology class that has a compact support and then is being decomposed over its support and pushed forward. So let me say a little bit about the machinery for this. So let's fix a finite group G for the remainder of this talk. And all the maps that I'll be talking about for the rest of this are probably going to be equivariant, so I might not say it. So let's define R of X to be the category of retractive G spaces. So it's things that look like this. It's going to be spaces Y that have an inclusion of X and that map down to X in such a way that this is the identity. And we should think about this as analogous to pointed spaces, right? If X was just a point, what a pointed space is it's the inclusion of a point into a space that then maps down to the terminal object in such a way that this is the identity. So what you're really doing with attractive spaces is you're just like replacing the point by whichever space you like. So if I like this space X, I'm going to say I want to look at all of those spaces that are based at like a full copy of X. So like a full thing of X sitting inside them. And you can stabilize this thing. Sorry, let me actually maybe just give a quick example before saying that. So given a vector bundle E to X, its fiber-wise Tom space, which I'll denote with the subscript X, is given by compactifying each fiber. So normally when I build a Tom space, right, I've got some vector bundle sitting over X, and then I take all of the fibers and I'm going to compactify all of them at some common point out at infinity. When I do a fiber-wise Tom space, I do a slightly different thing. I'm just going to take the fiber over X and I'm going to give it a compactified point at infinity. So now every single point at X, like they all have their own point at infinity along the fibers. And you can recover your ordinary Tom space by just gluing those all together if you want to. But this is a retractive X space and it's based at that new copy of points at infinity. So stabilizing, we get the following. I get this category that I call GOS of X. So this notation I stole from Carey Malkovich, but I think it'd been around before. So this is genuine orthogonal parametrized spectra over X. So that's a lot of adjectives, and I don't want that to be as terrifying as it looks. Oh, and there should probably be equivariant also somewhere in there. I guess that's in the genuine. So equivariant means like we're still doing things with group actions on our space. That's what that means. Parameterized means we're always working over the space X that we fixed. Orthogonal, don't worry about that. You have a smash product. And then genuine means we're stabilizing with respect to all representation spheres, not just the trivial ones. Okay. So given a map F from X to Y, we have a forgetful and pullback adjunction. So I can go from GOS of X to GOS of Y. And this is going to be basically I'll forget along this structure map down to a point. And I've got to map back the other way. It's basically given by taking something over Y and pulling it back to live over X. As a side comment, if you're coming from the motivic standpoint, these GOS of something spaces should feel like SH. This should be like a stable motivic homotypic category. Okay, so F upper star also admits a right adjoint. and this is called F lower star. And this is like a, if you look in the literature, like May Sigurdsson or Pohu or any of these people who worked with parameterized stuff, this is like a very mysterious object that they kind of say exists and then neglect to say anything beyond that point. The idea is that it should really feel like extension by 0 for sheaves. It should be some analog of that. So let me give an example of what lower star does. So if I from Z to X is a closed immersion, everything's equivariant still here. I could take just sort of the simplest possible thing, which is I'm going to take the 0 sphere over Z. So what the 0 sphere is, right, like we're living over Z, so Z is your point. So a 0 sphere is 2 copies of Z. And I want to include that into X in some way. And then I sort of want to smooth out that extra copy of Z to live over X. And what this ends up looking like is this ends up looking like a double mapping cylinder. So let me try to draw this. So I've got 2 copies of X here. I've got a copy of Z in the middle on both these things. And what I'm doing is I'm gluing these together along the complement Z. So the action comes in and it sort of acts level-wise. And when I do this, I see that this thing, I can collapse all of these points that are in the complement of Z. I can just push them down to the base. And I've sort of got this hollow interior right here. So when I glue everything down, I've got here's Z, and I've got this extra copy of Z that came from the top right here. So this is also the same as taking a Tom space of a normal bundle of Z and X and then forgetting this thing. So this is sort of like, this is like in Klein-Williams 2, they talk about this sort of thing, if you're familiar with that type of like intersection theory stuff. Okay, so in the interest of time, let me sort of speed up a little bit. So for any virtual bundle, vector bundle, E over X, we get what would be called a Tom transformation. So I get this map from GOXX to itself, and we denote it by this. And basically what it does is it takes any object that lives over X and it maps it to a fiberwise Tom space with this, or a fiberwise smash product with a fiberwise Tom space. So this is an invertible thing. And I can say, if I have complex K theory of X, I get a map to the Picard group of GOS of X by, I'm going to send some class E to just this thing at the sphere spectrum. So really just the suspension spectrum of this Tom transformation. And there's 2 cool things to say about this. The first one is that this is actually a group homomorphism. And the second thing is that this actually extends to perfect complexes of vector bundles. So what this is chain complexes of virtual bundles, which are quasi-isomorphic to bounded ones. And it already maybe feels like the abstraction has gone off the rails here, but this is like a very natural object to look at. So if you go back to like the OG Siegel paper about like equivariant complex K theory, he's really dealing with this. He's not doing perfect stuff, but he talks about, I have what I call a complex. It's like a very concise thing, which was just like a bounded chain complex of complex bundles or virtual complex bundles. So something that I can come back to at the end if people are interested is basically to any map F from X to Y, put any in quotes because I really want the kind of nice ones, we get an associated dualizing object. So we get something that Pohu calls CF. In our notation, it would be the Tom transformation of some cotangent complex at the sphere spectrum. And this is really an invertible spectrum living in the Picard group of GOS of X. So the reason that we want this is this allows us a treatment of duality in this context that's like strictly, it works in a much more generality than sort of what had previously been done in the literature. And this allows us to like flesh out the 6 functors formalism in this context a lot better. And in particular, it allows us to have push forwards. So now I can push forward cohomology classes up to a cotangent complex. Okay, so let me get some definitions on the board, and then I'll get some theorems up. So a definition is that the A cohomology of X twisted by some complex, I'll just write perf of X, is defined to be as follows. I'm going to take the sphere spectrum over X. I'm going to map it into the Thom transformation of A. And this is in GOS of X. So A really here should be any ring spectrum that lives over GOS of X. In particular, I could pull it back from any ring spectrum parameterized over a point. And we should remember that like being parameterized over a point just means you're living in like the actual genuine stable homotopy theory. So like any ring spectrum that we want equivariantly, we can pull back here. And another definition is for Z sitting inside of X, maybe some closed subspace, the everything up above that's compactly supported on Z is as follows. I'm going to have almost the exact same thing, but instead of the sphere spectrum over X, I'm going to push forward the sphere spectrum over Z. And map this. Okay, so we remember that this thing is like this fried egg looking space where I had this base copy of X right here, and I had this extra copy of Z. And why should this be cohomology with compact supports? Well, this base copy of X has to be sent where it has to be sent, because these are all based maps. But this extra copy of Z that I have here is able to be sent anywhere in this thing. So every point in Z, roughly speaking, is being sent to something in here. And that's sort of measuring a cohomology class on Z that like that's its support. Okay, so let me state the big theorem, and let me say theorem star here, because it's the second part of it is relying on stuff that's like almost done, but not completely done. So given an enumerative problem, so what I'll call an enumerative problem is maybe some bundle over, let me use M instead of X. So I've got some smooth manifold, I've got some vector bundle of the right dimension, I've got some sigma, and I've got some plus orientation data. And a ring spectrum A. The diagram commutes. So by this diagram, I mean, I'm going to take the cohomology of M twisted by E and supported on the 0 locus. I'm going to decompose it over all the points in the 0 locus. And then I'm going to push each of these forward down into a point. And then I've also got this sort of this other way to push forward. So I'm being kind of vague here, but here basically what I have is I've got some Euler class of my bundle, and I can decompose this thing over its support, and then I can push it forward. And what I get a sum here is a sum of local indices of points in my 0 locus. And then what I get over here is I get what I was calling an Euler number. And the star part of the theorem is that the following two things. The first one is that N of E doesn't depend on sigma. So this is telling me I have an Euler number that can be computed independent of the section. And now I just have to tell you what local indices are doing. And the second thing is that if I pick the right ring spectrum, then what I'm doing is I'm taking an enumerative problem, I'm orienting it in a specific ring spectrum that I like, and I'm saying I can get something in pi naught of that ring that is a global information is sum of local information. So if I use like a nice looking ring, so this is bad notation to start with A and then use A in a different context. But if A is something like the Eilenberg-MacLane spectrum of the Burnside-Mackey functor, then here's what the local index looks like. It's going to be, I'm going to take, is this what I want? Sorry, I should really say, it's going to be, I'm going to transfer from the isotropy group of P up to G, the element 1. And this is going to give me a coset corresponding to the isotropy. So this might look complicated, but this is basically saying, this is just encoding the orbit of the point P under G. So that you get this big corollary really, which is that if I want to answer some enumerative problem under equivariance, what I get is I get a sum over local indices, and these local indices are just including the isotropy of the solutions together with multiplicity really. So local data is really isotropy plus multiplicity. Okay. So with that, I can state the big corollary of this theorem, which is we can actually answer this question now about lines on a symmetric cubic. So for any symmetric cubic over C, it's 27 lines come in the following orbits. So I've got one block of lines that lie in one orbit. They all have isotropy group C2. So S4 right has 24 elements in it. C2 has 2. So this gives you 12 lines. I've got another collection of lines that has the exact same isotropy. So I have another collection of 12 lines. And then the last collection is I've got 3 lines that have isotropy D8. So this is like the payoff for all this formalism. Like the formalism allows us to state this sort of very complicated result about decomposing cohomology classes and doing all of this nonsense. But what this means ultimately is that like I've got this number that didn't depend on the choice of section. And what this number should be is it should be, you know, exactly this global count, right? And what I want to do is I want to say, okay, well, how do I compute this number? I should pick a specific section that I like, push this forward and compute all the local indices. And this is actually like a tremendously easy process once you've set it up. You're saying pick a symmetric cubic that you like and count the local indices of these things, meaning count where the lines are being sent under an S4 action. So if you have a cubic surface like the Fermat or like the Klepsch where you know the equations for the lines, you can literally just like write down the equations and start acting on them via S4 and see what the orbits are. And then once you've recorded the orbits, that'll be true for any symmetric cubic. Okay, so I'm at time, but let me just sort of say like, the payoff of this is like, this is one corollary, but you can do this basically for any enumerative problem with a group action. So now we know we have this well-defined solution. So the idea is just to set up an enumerative problem under the presence of symmetry and then count the sort of things that you're seeing. And then you get like a cool theorem that states like that symmetry plays well with enumerative stuff. Yes, that's all I have. Thank you so much.
All right, let's all thank Tommy. And then a note about the recording. So today's recording is just going to be sent to seminar participants. So feel free to ask any questions now while the recording is still going. I'll also turn it off in a few minutes. And if you want to ask a question, then that's also totally good as well.
Sorry. So I have a question. So this computation you did, you actually did it in what cubic setting, or
No, yeah, so none of this is motivic. Yeah,
Okay.
that's kind of the cool thing about this is it. I don't know how long of a question. The short answer, it's not motivic. The long answer is there's this philosophy that like once you've mapped something forward along the cycle class map, and you care about the Turing classes of an algebraic bundle, you actually care about the Turing classes of the underlying topological bundle. So it suffices to work with the topological homotypic class of that section. So a lot of these things should just be able to be done topologically without reference to algebraic stuff.
I see. Okay. Because we don't know actually some result like this, that the relation between the other class and the local indices, right, in the motivic context. Not yet.
We know the theorem of Bachmann and Wickleburn, so we know like the Euler class is a sum of local indices.
Okay, I see.
I guess there is this sort of like, is it defined over Z thing? But
okay.
yeah.
Thanks.
So, oh, sorry, can you hear me?
Yeah.
Okay. So I'm kind of forgetting how this goes sort of classically, but like, let's say you're doing, you know, you're trying to like compute indices of like vector field, trying to do this like Poincare style calculations. In those situations, you can kind of do something geometric, right? Where you sort of like pick a vector field and look at sort of the singularities and compute some index that way. So I'm wondering, like, I don't know, is there anything at all analogous in this kind of situation, or?
Yeah, 100%. Yeah. So if I took, if I was in this setting, let's say, I could take the tangent space of X, if X were a manifold, right? And I could say, I've got any section of my tangent bundle, which is an equivariant vector field. And then you can do this exact same story. So I can say, I could push this forward globally. That would give me an Euler characteristic of my manifold, like an equivariant one in the Burnside ring. Or I could look at the local indices and push these forward, and I would get like a sum of local indices of an equivariant vector field. So there's this work of like Wolfgang Luke and I think Jonathan Rosenberg about this type of stuff. And this is just like more formalism that kind of fits that sort of story. I'll also say you can get equivariant Lefschetz numbers in this setting as well, if you're interested in that.
Also, one thing I've always been curious about in this, I guess this isn't really like technically A1 enumerative geometry, right? As you said, this is kind of like you reduced it to doing something topological, but how, at the end of the day, how do you sort of extract a number from these things? I guess is what I'm wondering. Sort of at the end, you have these three classes, and I guess they sort of have like multiplicity built into them. How do you see that multiplicity or sort of extract?
Yeah, there's always this map from the Burnside ring to the integers that takes like, I guess you'd call it the rank or something like that of your associated orbits, and you would get 27 under this thing. Just like when you're taking the rank of something in Grothendieck-Witt, you would get 27.
Okay, I'll perhaps stop the recording here.